Assalamu alaikum. Dear learners, I hope you have watched the previous videos and have practiced the instructions described in that video. In this video, I am going to talk about two very important instructions that are timer and counter. I have mentioned it several times in the previous videos that sequence control can be implemented through elements that exhibit some kind of memory, and timers and counters are the most basic and important such elements. So let's first see what timers are and how you can use them. Well, like most of the PLCs, Allen Bradley Micrologix and SLC PLCs also have three different kind of timers. The first one is called the delay on timer, which starts timing when run conditions become true. The second one is called the delay off timer that starts timing when run conditions become false. And lastly, the retentive timer is similar to a delay on timer with an exception that the timer will start timing from a point from where the timing was halted due to any reason. I'll talk about it in more detail in a while. Each timer has a three-word address, and I should mention right over here that Micrologix 1000 PLC has only one timer, whereas Micrologix 1100 and above and SLC series PLCs have one default timer, whereas several other timers may also be programmed using generic data files. I'll clear this point when I'll come to the simulator. Anyhow, no matter what kind of timer we are using, it will have a three-word address. Of these three words, the most significant bits of word 0 are used to store status of the timer. Bit 15 shows whether the timer is enabled or not. That is, if the run conditions are true, the timer will be enabled and this bit will be true or 1. Otherwise, it will be 0 and timer will be disabled. Bit 14 shows whether the timer is currently timing or not. So, if the timer is enabled and the timer hasn't finished timing, this bit will be true or 1. However, if the timing has been completed, this bit will go false and the next bit, that is the bit 13, will become true. Bit 13 shows whether the timing has been done or not. All other bits of word 0 are not available for use. The next word, that is word 1, is used for storing the preset value, and the last word, that is the word 2, is used for storing the accumulator value. The accumulator word may be addressed using the addressing format as shown over here. T4 over here points to the timer data file and 0 is the element number. After element number, you may write 2, that is the word number for accumulator, or you may write ACC to access the accumulator word. Well, accumulator, as the name suggests, accumulates the time elapsed since the timer has started timing or it was last reset. Once the timer is enabled, the timer will automatically start timing and the contents of accumulator are continuously updated. So, for how long the timer will keep on timing? Well, it will keep on timing unless the accumulator value reaches the preset value. So, as soon as the accumulator value reaches the preset value, the timer timing bit will go 0 and the timer done bit will go high. You may use these bits in your program to start or stop certain outputs. The addressing of preset word is similar to that of the accumulator, with an exception of last word as being 1, or you can use PRE. Now you might be wondering that how the accumulator contents are changed or updated so that they reach the preset value and the timer signals that timing has been completed. Well, a third value associated with any timer is called the time base. It determines the timing interval after which the accumulator will increment its value by 1. Typically, you can select the time base value as 0.01 seconds, 0.1 second, and 1 second. However, different processor might offer you different list of time base values to choose from. Now, if you want the timer to time for, let's say, 5 seconds, then selecting the time base value as 1 and preset value as 5 will do the job. In this case, the accumulator will increment its value by 1 after every 1 second. And after 5 seconds, the accumulator value will be equal to preset value and the timer will stop timing. Or alternatively, you may choose the time base value as 0.1 and preset as 50. Now the accumulator value will increment by 1 after every 0.1 second, and hence after 50 increments, it will reach the preset value, or in other words, after 5 seconds the timer will signal the end of the timing process and raise the timer done bit. Programmatically, the on delay timer block will look like this, and whenever you use it, you have to specify the timer, that is the data file in which the timer will be stored, the time base value, and the preset value. Additionally, you may initiate the accumulator value to any positive non-zero value, but keep in mind that whenever you'll reset the timer in your program, the accumulator value will go to 0. Specifically for the on delay timer, the timer done bit, that is the bit 13 of word 0, will be set when the accumulator value has reached the preset value and will be reset or go 0 if the run conditions are false or if the timer is timing. The timer timing bit, that is the bit 14 of word 0, will be set when the timer is enabled and the accumulator value is less than the preset value. It will be set or go 0 if the run conditions go false or the timer has completed the timing. Lastly, the timer enable bit or the bit 15 of the word 0 is set when the run conditions are true and reset when the run conditions are false. On the contrary, the off delay timer, although will have a similar block and require same inputs for its working, the word 0 bits will behave differently than the word 0 bits of the on delay timer. In this case, the timer done bit will be set whenever the run conditions are true or run conditions are false and the timer is timing, and will be 0 if the accumulator value has reached the preset value. The timer timing bit will be set when the run conditions are false and the accumulator value is less than the preset value, and it will be reset when the run conditions are true or the done bit is reset. Lastly, the timer enable bit will be set when the run conditions are true and will be reset if the run conditions are false. The off delay timer can be very confusing for the first time users. Therefore, it is highly recommended to practice it through the simulator to grasp the workflow of this timer. The last type of timer is the retentive timer, and it is exactly similar to the on delay timer. The exception over here is that even if the run conditions go false or the PLC loses power or its mode is changed to any other mode from the run mode, or even if any fault occurs, the accumulator value of this timer will not reset to 0. It will be maintained, and whenever the timer is enabled again, the accumulator will start incrementing from where it stopped. You can say that this timer times the cumulative time for which it has been enabled. You can compare this table with that of the on delay timer and will find only one difference. That is, the timer done bit will reset only when the reset command is executed. Otherwise, once the timer has completed timing, or even if the timer is timing, there is no way to reset the contents of the accumulator, and hence the done bit as well. The reset instruction may be used with on delay timers or retentive timers to reset them whenever certain conditions are met. Moreover, the same reset instruction is used to reset counters as well, which we will see in a bit. The reset instruction's address will tell it which timer or counter it should reset when its run conditions become true. Now let's move to the simulator to see the timers in action and see how a reset instruction works. So over here I have drawn a simple ladder diagrams to exhibit the working of the on delay timer. Let me first explain that what is happening over here, and then we will run it to see that actually what is happening. In the very first rung, I have this start button, which when turned true will turn on the timer or will enable this timer. In this timer, you can see that the address is P4:0. That is the timer data file number 4 and its element number 0. Now this address will be used to store the data of this timer. Secondly, I have chosen the timer base as 1. You can choose this value from the provider list. You can double click on this value to drop down the list and you can choose any value over here. And for the preset, I have entered 15. This means that after every 1 second, the accumulator content will increment by 1 and will keep on incrementing up till it reaches 15. Once the accumulator value reaches 15, the done bit will be set and the timer timing bit will be reset. So as long as the timer is timing, this timer timing bit will be set, and hence this rung will have true conditions. And at the end of this rung, I have attached an output coil. So this output coil will remain on until this timer is timing. And as soon as this timer completes its timing, the timer timing bit will go off, and hence this output will go off as well. Now in the third rung, you can see that I have used the done bit of the T4 timer. Now as soon as this timer will done timing, this done bit will go high and the conditions in this rung will become true. And now what is on the output side of this rung? Now there is one output coil, it will turn on, and there is another timer that will be enabled. So as soon as this timer is enabled, it will start timing. Now you can see over here that this timer has an address of P9:0. That is the ninth data file and the 0 element. Now this data file will be used to store the status of this second timer. And over here you can see that I have selected 0.01 as the time base. So after every 0.01 second, the contents of the accumulator will increment, and they will keep on incrementing unless they reach the preset value, that is 1500. And if you can multiply the time base with the preset value, you will reach at 15. So this timer is once again going to time 15 seconds. Now as long as this timer is timing, the corresponding timing bit will remain on, and hence a second output will remain on, signifying that the second timer is timing right now. In this rung, I have used the done bit of the second timer, and as soon as the second timer completes its timing, the done bit will go high, and when this bit will go high, what will happen? It will turn on another output, and it will additionally reset the first timer, that is the T4:0 timer. So I've used a reset instruction over here. So now let's see that what happens. So I'm going to run this code, and now the PLC is running. So right now the start button is off, so nothing is happening. So as soon as I toggle this start button to on, you can see that the timer 1 has started timing and the timer timing bit has gone high, and similarly this output has gone high. So this timer will keep on timing unless it has reached 15, and now it has reached 15, and you can see that the done bit has gone high and the timer timing bit has gone low. Over here the done bit has gone high, and now you can see that this output has gone high, and similarly this second timer has gone high as well. Now it has completed its timing as well, and what happened is as soon as this timer finished its timing, the done bit went on and it reset the first timer. Now you can see that once again the cycle has repeated, and now this timer is timing. Right now the timer timing bit is high, and as soon as it will reach 1500 over here, the done bit will go high and this reset instruction will be executed, and this first timer will be reset and it will start counting once again, because right now the start switch is on. But if I turn off the start switch, the whole cycle will discontinue or will be turned off. So I hope that you have understood that how you can use the timers and how you can use their certain bits, that is the timer timing bit and the done bit, to control certain outputs. So now let's move back towards the slides and see what counters are and try to understand them as well. We hope that you have understood the working of timers. Now let's talk about counters, which are as important as timers. In Micrologix and SLC PLCs from Allen Bradley, there are two kinds of counters: the count up counter and the count down counter. Both counters count the false to true transitions of the rung conditions. However, the count up counter will increment its count whenever a false to true transition is detected, whereas the count down timer will decrement its count. Like timers, counters also use a 3-word address to store the information related to its working. And once again, Micrologix 1000 PLC has only one counter file, whereas several counters can be used with higher Micrologix processors and SLC processors. Anyways, the word 0 of the counter file will contain the status of the counter. The bit 15 is set if the count up counter is enabled, whereas for count down counter, bit 14 is set. Bit 13 or the done bit will signal when the counting has been completed. that is, the accumulator value has reached the preset value. I'll explain the rest of the bits in a while. Just like the accumulator of the timer, the accumulator over here will contain the number of false to true transitions that have occurred since the counter was reset. The addressing format is also similar to that of the timer. The preset value for the counter will be the value which, if reached by the accumulator, the done bit will go true, signaling that the counting has completed. So, for every false to true transition of the run conditions, the accumulator value will increment, and when it will reach the preset value, the done bit will be set. The range of preset values, and hence the values that an accumulator can store, is from negative 32,768 to 32,767. What happens beyond this range will be explained in a bit. So the count up counter will start counting from 0, and for every false to true transition of the run conditions, the accumulator content will increment by 1 unless it reaches 32,767. Now, if one more false to true transition is detected, the accumulator value will wrap back to negative 32,768, and the overflow bit, that is the bit 12 of the word 0, will be set. After that, the accumulator will keep on incrementing its count in a normal fashion. On the contrary, the count down counter will start counting from 0 and will decrement its count in the accumulator by 1 whenever a false to true transition of run conditions is detected. Now, if the accumulator content reached negative 32,768 and one more false to true transition is detected, the accumulator content will wrap up to 32,767, and the underflow bit, that is bit 11 of the word 0, will be set. After that, the counting will continue in the normal fashion. The only way to reset the accumulator content to 0 is through the reset instruction. Otherwise, the accumulator content will keep on incrementing or decrementing even if the preset value has been reached. The count up counter block will look like this and will require you to specify the data file addressed as C followed by the data file number, colon, and then the element. Moreover, the preset value is also required. Now, whenever the run conditions are true, the count up enable bit will be set, and if the conditions are false or if a reset instruction is used, this bit will be reset. The done bit, that is the bit 13 of the word 0, will be set when the accumulator value is equal to or greater than the value of the preset, and will be reset if the accumulator value is less than the preset value. And as for the overflow bit, I have already explained when it will be set. On the contrary, the countdown counter will have the countdown enable bit set when the run conditions are true, or will be 0 if the run conditions are false or a reset instruction has been used. As for the done bit, it will be set if the accumulator value is greater than or equal to the preset value, and will be reset if the accumulator value is lesser than the preset value. In other words, its working is exactly same as that of the count up counter. Lastly, the underflow bit has already been explained that when it will be set. Now let's move to the simulator once again to see the counters in action. Okay, so this is a simple ladder diagram which I have generated to explain the working of the count up and count down counters. Let me explain that what is happening over here, and then we will run it to see that what happened. In the very first rung, I have used a switch that is labeled as sensor A. So whenever this switch will transition from false to true, the counter attached at the end of this rung will count. Now for this counter, you can see that the address is C5:0. That is the default counter. And the preset value has been set at 8. Normally, the counter will start counting from 0, but you can have accumulator value other than 0 if you want the counter to start counting from some other value. But note that whenever you will reset this counter, the accumulator value will be reset to 0. In the second rung, I have used another switch and labeled it as sensor B. So whenever this switch will transition from false to true, the countdown counter, that is at the end of this rung, will start counting. And in the countdown timer, you can see that I have used the 9th file as the address of this counter, and the preset value is 10, and right now the accumulator value is 20. So this counter will start counting from 20 and backwards to 10. So at the start, the done bit of this countdown timer will be true because right now the content of the accumulator is greater than the preset value. And when this countdown timer will keep on decrementing its accumulator value and will reach a value lower than the preset value, the done bit will become off or will be turned low. In the third rung, you can see that I have used a reset switch, and whenever this switch will go high, it will reset the first counter, that is the counter C5 colon 0. And in the last rung, I have used the done bit of the first counter, that is the count up counter, and when this counter will complete its counting, the done bit will go high and it will turn on this output. Now let's see that what happens when we run this code. So now the PLC is running. Right over here you can see that in the second rung, the done bit of countdown timer is on because the preset contents are lesser than the accumulator content. So when this countdown timer will decrement its accumulator value less than the preset value, only then this done bit will become off. So over here in the first rung, I'm going to turn on the switch, and you will see that this counter will increment its accumulator content by 1. Right now the accumulator contents are 5, and when I'll turn this switch on, the accumulator content has incremented by 1, that is, it is now 6. Right now you can see that the count up enable bit has turned on because right now this rung condition is true. But when this rung conditions go false, the accumulator value is still 6 and the count up enable bit has turned off. Similarly, I am going to toggle this bit 1 or 2 times so that the accumulator value reaches the preset value. Now, as soon as the accumulator value reaches the preset value, you can see that the done bit has turned on. And in the last rung, you can see that this done bit has the same address as this counter's done bit, and this output has turned on. Similarly, if I toggle this sensor, you can see that the accumulator contents will start decrementing. And whenever I'll turn this off and turn it on again, the accumulator contents will keep on decrementing. Keep note of the done bit that it is still on because still the accumulator contents are greater than the preset value. So as soon as the accumulator contents go below the preset value, the done bit will turn off. This third rung has a reset switch which, if turned on, will reset the counter number 5 colon 0. So let me turn this switch on, and you can see that this counter has turned off or it has been reset. But right now, as sensor A is on, that is why it is turning off and then on and then off and then on and again and again. So let me turn this off as well. And now you can see that the accumulator content has been reset to 0 and the done bit of counter 5 colon 0 has also been reset. So in this fashion, you can use the count up counter and count down counters to count the pulses that are coming on any input sensor. So I hope that you have understood the working of these counters, and now you can use these counters in your program to keep a track of different things that are happening. So that's all for this video. Thank you and take care.